Collinearity of Vectors. Welcome, everyone. Today, we are going to begin a new topic in vector algebra, the collinearity of vectors. To start off, let's look at what collinear actually means. In the context of vectors, when we use the term collinear, we are referring to vectors that act along the same straight line, or perhaps along lines that are parallel to one another. If you visualize this geometrically, it is quite straightforward. Two vectors are considered collinear if they are parallel to each other. Now, a very important point to keep in mind right from the start is that collinear vectors do not necessarily have to point in the exact same direction. They can be parallel, meaning they point in the same direction, or they can be antiparallel, which means they point in opposite directions. As we move through the next few slides, we will look at the specific mathematical conditions that allow us to prove this, and I'll show you how to apply this using components and real-world examples. Mathematical condition for collinearity. To start, we specify that we are dealing with two non-zero vectors. Let's call them vector A and vector B. We say these two vectors are collinear if one can be expressed as a scalar multiple of the other. In mathematical terms, this means that vectors A and B are collinear if there exists a non-zero scalar, which we will represent by the Greek letter lambda, such that vector B equals lambda times vector A. Now, it is very important to understand what this scalar lambda tells us about the relationship between the two vectors. The value of lambda determines the direction. If lambda is greater than 0, then the vectors A and B are collinear and they point in the exact same direction. However, if lambda is less than 0, the vectors are still collinear because they are on the same line, but they now point in opposite directions, or what we call antiparallel. Now that we have established the basic idea that collinear vectors lie along the same or parallel lines, let's look at the precise mathematical condition we use to prove this. As we will see in the next slide, this scalar relationship is the key to checking for collinearity using the individual components of the vectors. Collinearity in component form. Now that we understand the concept of collinearity and the idea of a scalar multiple from the previous slide, let's look at how we actually apply this using components. When we express our vectors in terms of their components along the x, y, and z axes, using those standard unit vectors I hat, j hat, and k hat, we can determine if they are collinear simply by comparing the ratios of their corresponding components. Let's write this out formally. Suppose we have vector A, which is a 1 I hat plus a 2 j hat plus a 3 k hat, and vector B, which is b1 I hat plus b2 j hat plus b3 k hat. As we established in the previous slide, for these to be collinear, there must be a scalar, which we'll call lambda, such that vector B equals lambda times vector A. If we substitute our component forms into this equation, we get b1 I hat plus b2 j hat plus b3 k hat equals lambda multiplied by the quantity a 1 I hat plus a 2 j hat plus a 3 k hat. By distributing that lambda, we see that the expression becomes b1 I hat plus b2 j hat plus b3 k hat equals lambda a 1 I hat plus lambda, a 2 j hat plus lambda, a 3 k hat. Now, for these two sides to be truly equal, the coefficients of each unit vector must match exactly. By comparing the coefficients of I hat, j hat, and k hat, we can derive three separate equations. We find that b1 equals lambda a 1, which means lambda equals b1 divided by a 1. Similarly, b2 equals lambda a 2, so lambda equals b2 divided by a 2, and finally, b3 equals lambda a 3, meaning lambda equals b3 divided by a 3. Therefore, we arrive at our practical test for collinearity. For two vectors to be collinear, the ratio of their x components, their y components, and their z components must all be equal to the same scalar lambda. This mathematical rule is exactly what we are going to use in the upcoming examples to verify if vectors are parallel or antiparallel. Real-world analogy. Now, to help you visualize this concept beyond just the numbers and formulas we've discussed, let's look at a real-world analogy. Imagine two cars traveling on a perfectly straight highway. First, suppose both cars are moving north. In this scenario, their velocity vectors are collinear because they are traveling along the same straight path and they point in the same direction. In terms of the math we just saw, this means our scalar lambda is greater than 0. Next, consider a different situation. What if one car is moving north and the other is moving south on that same highway? Even though they are heading toward each other, their velocity vectors are still considered collinear because they are still acting along that same straight line of travel. However, because they are heading in opposite directions, our scalar lambda would be less than 0. In both of these cases, the line of action, the actual path the cars are following, remains the same. This perfectly illustrates that collinearity is about the path and the parallel nature of the vectors, regardless of whether they point in the same or opposite directions. Now that we have this intuitive grasp, let's move on to some concrete, step-by-step examples to see how we apply this to actual vector components. Step-by-step examples. Now that we have understood the theory and the mathematical conditions for collinearity, let's put it into practice with our first worked example. On this slide, we are presented with example 1, where our goal is to verify whether two specific vectors are collinear. We have vector A, which is 2i-3j plus 4k, and vector B, which is 4i-6j plus 8k. To determine if they are collinear, we will follow a systematic three-step process. Step 1 is to identify the individual components of both vectors. For vector A, our components are a sub 1 equals 2, a sub 2 equals negative 3, and a sub 3 equals 4. For vector B, the components are b sub 1 equals 4, b sub 2 equals negative 6, and b sub 3 equals 8. Step 2 is the most crucial part. We need to calculate the ratios of these corresponding components. First, let's look at the ratio of the x components, which is b sub 1 divided by a sub 1. That gives us 4 divided by 2, which equals 2. Next, let's find the ratio of the y components, which is b sub 2 divided by a sub 2. That is negative 6 divided by negative 3, which also equals 2. Finally, let's check the ratio of the z components, which is b sub 3 divided by a sub 3. This is 8 divided by 4, which results in 2. Step 3 is to compare these results. As you can see, the ratio of the x components, the y components, and the z components are all equal to the same value, which is 2. This means our scalar lambda is equal to 2. Because we found a consistent scalar multiple, our conclusion is clear. The vectors A and B are indeed collinear. In the next slide, we will look at a slightly different scenario, where the scalar value is negative to see how that affects the direction of the vectors. Step-by-step examples continued. Now, let's build on the logic we used in the first example by looking at a slightly different scenario in example 2. This time, we are going to check for collinearity when the vectors might be pointing in different directions. Our given vectors are vector A, which is I plus 2j minus k, and vector B, which is negative 3i minus 6j plus 3k. Our goal is to determine if these two are collinear. Let's follow our standard three-step process. First, step 1, we identify the components. Looking at vector A, the components are 1, 2, and negative 1. For vector B, the components are negative 3, negative 6, and 3. Next, step 2, we calculate the ratios of these corresponding components. First, the ratio of the x components, which is negative 3 divided by 1, gives us negative 3. Moving to the y components, negative 6 divided by negative 3 gives us negative 3. And finally, for the z components, 3 divided by negative 1 also results in negative 3. Now, for step 3, we compare these ratios. As you can see, all three ratios are exactly equal to negative 3. This means our scalar lambda is negative 3. To reach our conclusion, because we found a consistent scalar, the vectors are indeed collinear. However, notice the sign of our lambda. Since negative 3 is less than 0, these vectors are antiparallel, meaning they point in exactly opposite directions. This perfectly illustrates the point we discussed earlier regarding negative scalars. Common mistakes to avoid. Now, before we wrap up our lesson with the final summary, I want to pause and highlight some common pitfalls. Even if you understand the concept of scalar multiples, there are 3 specific areas where students often lose marks in exams. First, be careful about ignoring the sign of your scalar. It is a very common mistake to assume that collinear vectors must point in the same direction. However, as we saw in our second example on the previous slide, a negative lambda still indicates collinearity. If your lambda is negative, the vectors are simply antiparallel, meaning they point in opposite directions, but they are still acting along the same line. Second, we need to address a mathematical constraint when using the ratio method. When you are calculating the ratio of the x components, such as b sub 1 divided by a sub 1, you must be mindful of 0. If any component of vector A is 0, for instance, if a sub 1 equals 0, you cannot perform that division. In this specific situation, for the vectors to remain collinear, the corresponding component of vector b must also be 0. You cannot have a direction in one vector that is missing in the other if they are to remain parallel. Finally, do not confuse the concept of collinearity with the concept of equality. 2 vectors can be collinear without being equal in magnitude. For 2 vectors to be exactly equal, our scalar lambda would have to be exactly 1. But for collinearity, we don't need lambda to be 1. We only require that some non-zero scalar lambda exists. Keep these distinctions in mind as we move to our final slide to review the key takeaways. Key takeaways. First, let's revisit the fundamental definition. Remember, we say 2 vectors are collinear if they lie along the same line or parallel lines. This means they can be either parallel, pointing in the same direction, or antiparallel, pointing in exactly opposite directions. Second, let's look at the scalar condition, which is the algebraic heart of this topic. As we discussed in our earlier slides, 2 non-zero vectors, vector b and vector a, are collinear if there exists a non-zero scalar, lambda, such that vector b equals lambda times vector a. This simple equation is what allows us to scale one vector to match the other. Third, we have the component condition. When you are working with vectors in their component form, using the I, j, and k unit vectors, you can verify collinearity by checking the ratios of their corresponding parts. Specifically, the ratio of the x components, the ratio of the y components, and the ratio of the z components must all be equal to that same scalar lambda. In other words, b sub 1 divided by a sub 1 equals b sub 2 divided by a sub 2, which equals b sub 3 divided by a sub 3, all equaling lambda. Finally, don't forget the importance of the sign of lambda when determining direction. As we saw in our examples, if lambda is greater than 0, the vectors are pointing in the same direction. However, if lambda is less than 0, the vectors are still collinear, but they are pointing in opposite directions. All right, we have reached the end of our lesson. Before we wrap up, let's quickly recap the key takeaways from today's session on the collinearity of vectors to ensure everything is clear in your mind. Keep these points in mind as you practice your problem solving. Great job today!